Hello and welcome to the Chemistry Academy. In this video we're going to go over the colour of organic molecules in relation to the Advanced Higher Chemistry course. Now this is actually very similar to the colour of transition metal compounds, but the energy gaps we talk about are different, so that's the only real difference around the colours in transition metal compounds versus organic molecules. It's just where the electron transitions are occurring and what energy gaps we referred to. So hopefully if you're clued up on the colour of transition metal compounds, then this will be pretty straightforward for you. So the reason that some organic molecules are coloured is because they are absorbing wavelengths of light within the visible region of the electromagnetic spectrum. So if substances aren't absorbing energy in the visible region, then that's when they don't have a colour. So the only reason that we see them as being coloured is because there's visible wavelengths of light that are being absorbed or removed by the molecule and then ends up presenting as the complementary colour to us. So we'll get into that in a minute. But like I said, it's all to do with electrons being promoted still, much like when it's to do with the colour of transition metal complexes. But in this instance, we're talking about electrons being promoted from the HOMO to the LUMO. If you watch my video on molecular orbital theory, then this will make a bit more sense to you. So if you've not watched that yet, you might want to go back and watch it before you get further into this video, because it'll help make the rest of this make more sense. But remember, when it comes to molecules, we have molecular orbitals as opposed to atomic orbitals when we look at atoms. And we have bonding orbitals and anti-bonding orbitals. The HOMO stands for highest occupied molecular orbital, so that's the highest energy level molecular orbital that has electrons in it. So if you look at one of your molecular orbital diagrams, you can identify the HOMO by looking to see which orbital highest up has got electrons in it. That will be your HOMO. Because remember, the orbitals are also placed in order of increasing energy. So as we go from down here to up here, they are increasing in energy. The LUMO is the lowest unoccupied molecular orbital, and that's the lowest down molecular orbital that doesn't have any electrons in it. So in this diagram, this is our LUMO here, because there's no electrons in that, and that's the lowest energy molecular orbital that doesn't have electrons in it. So it's as straightforward as that, really. Highest occupied and lowest unoccupied. Now when it comes to the colour of organic molecules, it's this gap here that is the important one, because that's where the electrons get promoted from and to. So electrons will get promoted from the HOMO to the LUMO, and that energy gap there is the energy that is absorbed when those electrons get promoted. The wavelength of that energy then equates to will then determine what colour the molecule or the substance appears as. So if this HOMO-LUMO gap is large, then it means a smaller wavelength of light will be absorbed when the electrons do get promoted. If that energy gap is small, then it's a higher wavelength of light that will be absorbed. So just remember, energy and wavelength are inversely proportional. So if the energy is high, the wavelength's low, and vice versa. If the energy is low, then the wavelength will be high. So when we're looking at the colour of organic molecules, it's this HOMO to LUMO gap that's important, because the energy of that gap will determine what wavelength of light is absorbed, and then that then determines what wavelength of light that we actually visibly see. So if you are asked in an exam or to explain why colour occurs in these organic compounds, this is the sort of thing that you would want to write. So again, light energy is absorbed by the molecule, and when that light is absorbed, electrons are promoted from the HOMO to the LUMO. If we compare this to the transition metal complex colour theory, that when that light is absorbed, the electrons get promoted within the d orbitals. That's what causes the colour. So it's the same instance, light's being absorbed, electrons are getting promoted. But like I said earlier, it's just where the promotion's happening is different. So in the transition metal substances, it's in the d orbitals. In organic molecules, it's within the molecular orbitals, going from the HOMO to the LUMO. So when those electrons get promoted from the HOMO to the LUMO, specific wavelengths of light are absorbed in order to undertake that promotion. Like we've kind of talked about already, if that energy gap is high, it'll be a low wavelength of light that's absorbed. If the energy gap's low, then it's a higher wavelength that's absorbed. That specific wavelength of light is then absorbed by the molecule, and all the other wavelengths that are not absorbed are transmitted or passed through. And it's the combination of all the transmitted wavelengths that combine to give us the complementary colour that we see. So this is where your colour wheel in the data booklet is really helpful, because you can look to see what wavelength of light is absorbed, and then therefore what the complementary colour will be. So you're looking to see which colour is opposite. So if I just grab my data booklet here. So if we look at the colour wheel, if a molecule is absorbing yellow-green light in order to promote the electrons from the HOMO to the LUMO, then it will appear as violet in colour, because that's the complementary colour on the colour wheel. Okay, so your colour wheel is your best friend when it comes to colour. The part of the molecule that's responsible for absorbing visible wavelengths, like I mentioned earlier, it will have a visible colour if it's absorbing wavelengths within the visible region. The part of the molecule that absorbs those visible wavelengths of light is known as the chromophore. So the chromophore is the part of the molecule that essentially causes the colour of the molecule. If the chromophore wasn't there, then it wouldn't have a colour. Okay, so the chromophore is the thing that absorbs the visible wavelengths of light. If we then look at what affects this HOMO-LUMO gap, because that's what then essentially causes the different colours of different substances, because like I said before, the energy gap between the HOMO-LUMO is what determines what colour it'll be. It's the length of the conjugated system that's important when it comes to the actual energy gap between the HOMO and LUMO. So a conjugated system is a sequence of alternating double carbon-to-carbon bonds, essentially. So you can see there's a conjugated system here because these double bonds are alternating. So this has got a conjugated system of 4 pi bonds. This has a conjugated system of only 3 because there's a hydroxyl group at the end, kind of breaks it off. So this is a longer conjugated system than this one. If your conjugate system is longer, you will have a smaller HOMO to LUMO gap. So the longer the conjugated system, the smaller this gap becomes. And therefore you end up absorbing higher wavelengths of light. So that then changes the colour that you see. So this molecule here would absorb higher wavelengths of light than this one here, because this has got a longer conjugated system, so it's got a smaller HOMO-LUMO gap, so higher wavelengths of light will be absorbed by it. So that these two molecules would have different colours because they have different lengths of conjugated systems, which then leads to different HOMO-LUMO gaps, which then leads to different wavelengths of light being absorbed, and therefore different wavelengths of light being transmitted to give you your different complementary colours. If we just look at a couple examples of molecules here that I've got, I'll put them up on the screen. So we've got 2 molecules here. We've got lycopene and vitamin A. Lycopene is a red colour. If you were to look at anything that contained lycopene, it would have a reddish colour. Vitamin A gives a yellow colour, so anything with vitamin A in it looks a bit yellowish. Now if we look at why the colours of these molecules are different, again they've got different lengths of conjugated systems. So if we look at the conjugated system for lycopene, so if I just highlight here the alternating double carbon-to-carbon bonds, you can see the length of that is quite long. The double bonds at the ends aren't alternating. There's too much of a gap there for them to be part of the conjugated system. So the double bonds at the end of the molecule aren't in it. And then if we look at the conjugate system in vitamin A, we can see that is quite a bit shorter. Okay, so that means that the lycopene would have a smaller HOMO-LUMO gap, and then therefore the vitamin A would have a higher HOMO-LUMO gap because its conjugate system is shorter. That means then that the lycopene is going to absorb higher wavelengths of light because its HOMO-LUMO gap is smaller. Remember, it's opposite. And then therefore the vitamin A is going to absorb lower wavelengths of light because its conjugate system is shorter, so the HOMO-LUMO gap is higher. if we look at then what wavelengths of light are actually being absorbed by the molecule, if we look at the colour wheel, so if we look at lycopene, which is red, we can see that if something is appearing red, it's absorbing blue-green light, so that's between 500 and 490 nanometers. And for the vitamin A, because it's yellow, that means it's absorbing blue light, which is 435 to 480. If we then compare that to what we'd written already about which wavelengths of light would be absorbed, then it fits what we hypothesized based on the length of the conjugated system. So as you can see, we'd already noted that the lycopene would be absorbing higher wavelengths of light, which it is compared to the vitamin A, because 490 to 500 nanometers is higher than 435 to 480 nanometers. So if you do get a question on the colour of organic molecules and why their colours are different, then you're really wanting to focus on the HOMO-LUMO gap. Is it larger or bigger, and why? And then how that then affects the complementary colour that is observed. So I hope that helps. If you did find this useful, please give it a like. Don't forget to subscribe, and I'll see you again soon.